Okay, let's unpack this. You know how much processing goes into the food we actually eat?
Oh yeah, taking all those raw agricultural goods.
Fields of corn becoming cereal flakes or truckloads of fruit turning into juice.
Right, and all that transformation, it generates a ton of packaging.
Exactly. Cardboard boxes, plastic bags, those little trays, wraps. I mean, the list just goes on and on.
And then trying to get a handle on the sheer volume of that packaging waste, maybe across a whole industry or even, globally,
Way.
feels like this massive complex puzzle, doesn't it? How do you even begin to estimate something like that accurately?
Yeah, like simple counting or just weighing stuff at the end. It doesn't really cut it, does it?
Hmm.
Especially with production lines running constantly, different products.
Not really. It's too varied, too dynamic.
Exactly. It feels kind of overwhelming, almost like trying to measure a river just by, I don't know, looking at the surface.
That's a good analogy, yeah.
So this deep dive, looking into your source material, it got us thinking, is there a more precise way, a better way to approach this?
And that's where it gets really interesting.
Yeah.
The answer involves math, specifically calculus.
Calculus. Okay, hold on.
That's right. While you might be in class studying differentiation to find rates of change.
Or integration to find areas under curves. Yeah.
Exactly. Those aren't just abstract ideas floating around in a textbook. Integration, especially, gives us a really powerful framework for estimating that complex accumulating waste.
Calculus. But wait, how does finding the area under some curve help us figure out, say, how many plastic bottles come from a juice factory?
That's a fair question.
Yeah.
It's about it like this. The rate, the speed at which packaging waste is generated, it isn't always constant, right?
Okay.
A factory might make different products.
Yeah.
Maybe some need way more packaging than others, or production speeds might change during the day.
Right. Rush hours versus slower periods.
Exactly. Simple arithmetic, like multiplying, works okay if the rate is perfectly steady.
Yeah.
But it rarely is. With those varying rates, integration is actually what you need to find the total amount that builds up over a certain time, or maybe over the total amount of product they process.
Okay. So you're not just counting items at the very end. You're actually looking at the rate of waste happening as the processing occurs.
Precisely.
Yeah.
Yeah. Imagine we could define a function, something that represents the rate of packaging waste made per unit of product.
Like per ton of grain.
Or per hour of operation, yeah. And this rate might change depending on what's running on the line at that moment.
Okay.
Integration lets us sum up that constantly changing rate across the entire production run. So you could integrate over time from start to finish.
Or integrate over the total volume produced.
Exactly.
So if my waste rate function is WT waste per hour, where T is time, integrating WT from the start time to the end time gives me the total waste for that shift or that day.
You got it.
Yeah.
That's exactly right.
Yep.
Or, like you said, if you define the rate based on output, maybe WEV, waste per ton of processed grain integrating WV, over the total tons produced, gives you the total packaging waste for that entire batch. It's basically using that core idea of summing up infinitesimally small pieces, the little bit of waste from each tiny moment or each tiny bit of product to get the grand total.
Okay. Okay.
And this is super useful in complex industrial settings where those rates are always fluctuating.
That makes a lot more sense now. It's kind of like finding the total distance you traveled if your speed wasn't constant, right? You integrate the velocity function over time.
Perfect analogy, yes.
So here you're integrating the waste generation rate over time, or maybe over the amount produced.
Exactly. It lets you get a much more nuanced and accurate estimate than just grabbing an average rate somewhere and multiplying. That misses a lot.
Because you capture the peaks and valleys.
You capture the peaks, the valleys, all driven by different products or phases of production. This approach, straight out of calculus, it gives us a mathematical model that can actually handle the messiness of real-world industry.
Wow. Okay. So thinking about someone maybe studying calculus right now, what does this all mean for them?
Well, it means the integration you're learning isn't just theory for exams.
Right. It's not just abstract.
It's a genuinely powerful tool. You can use it to tackle tangible, real-world issues, like estimating this packaging waste from processed food.
That's fascinating, taking this, abstract math concept and using it to quantify a pretty major environmental and logistical challenge.
Absolutely. And getting a more precise handle on the scale of this waste using integration, that's crucial.
Crucial for what, though?
Well, for informing policy, For design packaging that's maybe more efficient or developing better recycling systems, you need good numbers first.
Makes sense. You need to know the size of the problem.
It just shows how math gives us the language and the tools, really, to understand and quantify the world around us, even the messy, complex parts.
So here's something to think about then. If integration can help us estimate packaging waste from food processing by modeling these changing rates,
Yeah.
what other maybe environmental or logistical problems? What else do you think could be accurately quantified, maybe even tackled, using the calculus concepts you're studying right now?
Hmm. That's a great question to leave people with. Something to definitely ponder next time you look at a really complicated problem out there in the world.